Right, so let's talk about some first order recurrence relations. And first of all, what I mean by first order is that we have a recurrence relation of the form an is some expression involving an minus 1 and possibly n as well, the number of the term that we're looking for. F here is just some function or some expression. And the first order part comes from the fact that it only looks back one term previous to get the next term. So it's only looking back one. And a solution for that simply means a whole sequence that satisfies the given relation for all values of n. The specified values of n are typically all positive integers or maybe all non-negative integers. And a general solution is an expression for an in terms of a alone, not a recurrence relation, but an expression for an in terms of n that tells us what the sequence will actually look like. And there's often some arbitrary constants in there. So that's the notion for general solution. It contains all the solutions in that expression. So let's look at some examples of first order sequences just to talk about them. So here's a first order recurrence relation because an is given in terms of an minus 1, just one previous term. It does involve n in there as well, no big deal. And this right here is called an initial condition. So we specify what it is at the start, and in fact we have to have an initial condition to be able to create a particular single solution as opposed to the general solution. But we could try and see what this is just to see how this turns out. So we're given a0. That would mean that a1 is equal to, well, 1, n is 1 here. So 1 times a0, 1 previous, so that'd be 1 times 1 is 1. a2, and here is 2. So that'd be 2 a1, which is 2 times 1, that's just 2. a3 is equal to 3 times a2, and so that's 3 times 2 is 6. And maybe you see what's going on here. This is very much like what we did to get the recursive definition for what? N factorial. a4 is equal to 4 times a3. So that's 4 times 6, that's 24, and that is 4 factorial. I won't prove it here, but it's pretty clear. I think you're probably convinced that in fact the solution with that initial condition is n factorial. In fact, while I won't go into detail here, the general solution would just start with a0 here, whatever it is, and the general solution is actually n factorial times a0, whatever a0 is. So there's our arbitrary constant, the a0. Here's another one here. You can play around with that if you like. an is n plus 1 factorial over an minus 1. So now we're dividing by the previous term. And a1 is 1. And I'll just give you some of the values. So we'll have 1, that's a1. a2 will be 6. I'm going to write them down here, and you can check them out. So you can pause and actually do some calculations and see if you get the values I do. All right, so I'll continue on. 4, 30, 24, that's a5, and a6 is 210. Okay? So, and you know, it continues on after that. All right, so a third one like that, an is the square of the previous term, an minus 1 plus 2. And if you do this thing here, you'll get, with this initial condition, minus 1, and then a1 is 3, a2 is 11, a3 is equal to 123, and it goes on like that, right? So again, you should check that, pause it, check it, see if you get those things. Right, so here's a general theorem that applies to a particular type of first order recurrence relation. So in this case here, the theorem says if b is a constant, then the recurrence relation, that's that very simple one right there, an is b times the previous term. So all we're doing each time is multiplying by b to go from one term to the next. Well, it has a general solution. an is equal to c times b to the n, where c can be an arbitrary constant. Any constant will give you a solution. If an initial value for a0 is specified, then the unique solution with that initial value is an is equal to a0 times b to the n. Right, so I'm going to argue why this is true using an inductive approach, mathematical induction on this one right here. But before I do that, let me just give an example. And I will tell you this is about one of the easiest problems that you could encounter on a test. If on the second test I do happen to decide to ask a solution here, then the unique solution of an is equal to, let's just pick a constant here, 5 an minus 1, where a0 is, I don't know, let's say 3, right? So this tells me that an, so this is a recurrence relation. I can't look at that and say what's a 21, right? I'd have to go through and find it. This form here tells me immediately how to get a21, or an in general. An in general would be 3, that's a0, times b to the n, there's our b, 5 to the n. Bingo, there it is. How quick, how simple. So why is it true? All right, so for the basic proof of this, let's consider the first term. The first term, actually the zero term if you like, a0 is some number. And let's assume that is a0, let me go ahead and say this, the statement an equals a0 b to the n when n equals 0 is just a0 is equal to a0 b to the 0, and since b to the 0 is 1, this is true, which is true. So the statement holds or is true for n equals 0. So that's the basis step. I didn't name the statement here p of n. If we were to name it, this would of course be p of n. But you will see the induction done without naming a statement, and just doing it the way I've done here. So now let's assume, so let's let k be an integer, k greater than or equal to 0. Why? Because I started at 0, not at 1 here. And assume the statement for n equal k, that is a sub k is equal to a0 b to the k. Then what is a sub k plus 1? Well, a sub k plus 1, I'm going to scroll up a little bit just so we can look at it, is given by the recurrence relation right there. So a sub k plus 1 will be given by that. Let me write it here. an is equal to b an minus 1. So if that's a k plus 1, I'll have a b, and I'll have an a. Well, 1 less is k. But we have assumed in our induction assumption that that's a0 times b to the k. So that's equal to a0 b to the k plus 1. So pk plus 1, or the k plus first statement holds. The k plus first statement holds. So by induction, an is equal to a0 b to the n for all integers n greater than or equal to 0. So I used an inductive proof for that. That proves that if it is a statement or a solution, this is what it has to be. And it's very easy to check that that is indeed a solution by plugging in to the original recurrence relation, since a0 b to the n is indeed equal to b times a0 b to the n minus 1. That's our an here. That's our an minus 1. That's true, so every one of these is indeed a solution. And what we have proved in the longer proof here is that a solution has to be of that form. So that's the unique solution if this is specified.